Welcome everybody to this ICE5 webinar about plant modeling and other usability features. My name is Per Salin. I'm the CEO of EQUA, and my co-presenters here are Jörgen Eriksson from our Gothenburg office and Mika Bulle from Finland. So I'll just show a few slides to start up with to introduce everything. And as you all know, this is the, I think, fourth webinar in the follow-up series around our ICE5 release, which is currently in beta, as many of you know. And this is the second webinar around the second focus area where we're looking at the building as a prosumer, thinking about buildings as energy users and producers in the future. So just a very brief introduction here. As we've discussed before at the earlier webinars, we're looking at a new energy landscape now, where more and more intermittent renewables are to be accommodated in our energy systems. And in our opinion, this will call for a lot more modeling and simulation. And it's also quite a sad state of affairs now, as we can see it in most countries, where most energy conversion plants for buildings, but also for larger districts and so on, are actually built essentially without any dynamic modeling at all. So they're just maybe computed in some steady state points, and then they're built and tested. And that's usually not the ideal way of creating a very complex technical system today. And the reason for this situation, we think, is has a lot to do with lack of tools, that there simply aren't any easy to use, scalable, robust, truly useful simulation tools out there for plants. And that's something that we would like to try to remedy. And one thing that is quite often overlooked when you look at a plant schematic, you just think about the plant itself. But the main reason usually for simulating a plant is perhaps not to look at the static behavior of the plant, but it's more to look at controls and see what is this plant going to be exposed to over a whole season, so to speak. And so the focus is very much on controls for finding motivation for selling projects around plant modeling and so on. And as we see it with the intermittent renewables and also access to more and more storage, both electrical and heat storage, this will create a lot of new challenges in finding optimal control schemes. And we think that a lot of the driving forces for doing more plant modeling will be coming from that direction. So today we have a couple of different parts of this presentation. Jörgen will kick off by introducing some of the new standard level plant and air handling unit features that you will find in ICE5. I will then pick up and talk a little bit about what we're trying to do on the advanced level in ICE5, around the ESPO plant mainly. And then Jörgen will sort of illustrate what I am trying to say by making a project example of how we think you can build a tailored plant efficiently and safely with these methods. After that, we shift focus a little bit and look a little bit more into the future. And Mika will show you some of the project work he's currently involved in that aims at using these new features for modeling not just single plants and buildings, but rather districts. And this is an area where we are focusing our R&D very intensively, and we hope to be able to bring you a lot of new tools in this area soon. Mika will also wrap up by going through some of the neat new features of ICE5 that hasn't really fitted into any other of the presentations. So we'll just show some miscellaneous features at the end. And then we will finish by a Q&A session. So, Jürgen, please start.
Yes, thank you. In IDA 5, we will have at least 3 new air handling units. Exhaust air with direct expansion heat recovery, liquid heat recovery with run-around coils, and ground duct for preheating and pre-cooling the air before it enters the air handling unit. The last one is not in the current, we haven't made a model of it yet available for you. So we start with the exhaust air with direct expansion heat recovery. If you look at the air handling unit, it's extremely simple. It's just the fan, exhaust air fan. Then it's connected to the plant actually. So the air system is connected to the plant. Then it's exhaust air again here. So I will go directly to the plant instead. So to use this, you just add air handling unit, and then you open the plant. Then you select direct expansion exhaust air heat pump. So select that one here. And this is a new version of our heat pump model. So it's with variable speed. It's more easy to implement because most of the compressor manufacturers give polynomials of the behavior of their compressors. So we use that, and then we make optimization, use optimization to create an entire model, including the evaporator and condenser. So it's not just adding the polynomials, it's a bit more work, but not very much. So we will have a database of such heat pump models. So if you build plant model, you can see the configuration. We have the air from the air handling unit connected to the heat pump, and the heat pump is then connected to the system by the tank, as all the heat pumps are in this ESPO plant model. The second air handling unit is liquid heat recovery with round-around coil. It looks almost the same as the standard air handling unit in the front page, but here you have a macro with the run-around coil. So here you have a coil on the supply side and one coil on the exhaust side. And in the circuit you have a pump, a valve that gives the mass flow, and a three-way valve that controls the efficiency of the system. So you get the correct supply temperature. When using this, it's very important that you make a sizing correctly. So you have to size them manually, actually. Round-around coils are very sensitive to the mass flows. So the mass flows times CP must be perfectly balanced to get the best efficiency. And here in the control macro, we just give a simple control. It can be more advanced if you have variable airspeed, for example, air volume supply. You might add some control of the flow to optimize the system continuously. And the last one is the ground duct system. It's not available yet in the program, but we will make it available soon. But so far the components are available, so you can make it yourself. I have a macro here before the heat exchanger. This is the ground duct. It uses bidirectional airflow, so the flow can go in both directions, but the air handling unit has only unidirectional airflow. So we have to add 2 converters to be able to use this in our conventional systems. So we found it all here under all, actually. Here we find the models. So we can look for it here, unit to bidirectional, the ground duct, and the bi to unidirectional. If I open the ground duct, it's divided in segments that can be configured different. So we can edit segment here, and here we have a small duct with a position of 1.5 meters below the ground, and a cross-sectional area of 0.2 square meters and a hydraulic diameter of 0.5.
Jürgen, I'm seeing here that we're already running a little bit out of time, so maybe you can
yeah. Sorry. So I just wanted to, and then you have to define the duct. Here it's a plastic duct, and you have to have the soil around it to make it work. So yeah, it's lots of things in a short time. The last thing I wanted to show to you is in 1 second, we have the possibility to add different distribution system levels. So normally it's just 1 level, but now you can have an advanced heating system, for example, distributed heating system. Then you can add some different temperature levels. For example, if you have a floor heating system, you might perhaps have at most 30 degrees into the floor, and then if you have radiators, you will have much higher temperatures. So if I select that there, this has already been presented in the previous section, actually. So if you do that, you can add a water radiator, for example, and then you can select here what system you want to connect it to. And of course, you can have more systems here. For example, floor heating. I just want to add it. And here we can select some other temperature levels. And then these can also be shown in the plant then if you build the plant model. Like this, then you have 2 circuits to the zone. Usually it's only 1 circuit. Yes, I will get back to Per here. So he will continue.
Okay, thank you, Jürgen. Actually, right, I was just looking where I was with my slides. Sorry. So now the building plant models in eighties has been quite problematic in the past, and our ambition now is to simplify it quite a lot. And one of the reasons that this has become so important is that we've actually done some benchmarking and testing, comparing eye-to-eyes plant modeling facilities with those of other Modelica programs. And it turns out that we're doing really, really well in these tests. So this, for example, is a relatively simple plant model that we have simulated both in IDA and an identical plant in Open Modelica, which is one of the open source Modelica tools. And if you run this for a while, you can see that in IDA, I think it's for a year, it takes 21 seconds to run this plant, and in Open Modelica, it takes almost a half hour. So that also for quite small plants, there is a considerable difference in speed. And if you make the model larger, and this is not a huge model, but it's still a significantly larger model, it's a district heating network. Excuse me, my phone is ringing here. With 200 simple building models, So these are simplified building models. I think about 20 equations in each model, 900 pipes connecting these buildings, and this amounts to a total of about 82,000 equations. So it's a sizable model, but it's not huge. And if you simulate this system in IDA for a whole year, it takes some 20 minutes or so. So that's quite doable. And we've also scaled it in IDA to about 40 times this size easily. And then you start to approach the sizes of real district heating networks. That's not a problem. And whereas in the main sort of the main leading Modelica tool, Daimler, it takes more than an hour to simulate this system for just a day. And we weren't actually able to simulate 2 copies of this system in in Daimler on that machine because it ran out of memory. So there's a distinct difference in scaling properties there, which we think is very interesting, and we want to pursue this and make plant modeling easier to use. Because as many of you know that have tried this in IDA ICE in the past, it's been quite problematic. And most of the reasons for this are actually relatively small things that we haven't really focused on making this easy for people in the past. And there's been a lot of historical models that have been making the whole operation a little bit more complicated as well. So I will show you a little bit about this here. Trying to look on time as well. So as Jürgen mentioned, and as or maybe didn't mention it actually, but in ICE 5, the old familiar plant model has been replaced by what we call the ESPO plant. I'm pretty sure most of you have come across the ESPO plant before because it's been in IDA for quite some time, but it's not been sort of a default option before. And we're still doing this a little bit carefully. So if you do build plant model here, you actually get to the old, very super simple IDA plant, and you have the same situation. We start from the same situation, but in a different package. In the ESPO plant, the purpose of the ESPO plant is to be able to very quickly experiment with various configurations of systems. So I dragged in a flat plate solar collector. Obviously, you have to give some parameters to these in reality and so on. I'm not spending time on that now. I dragged in a heat pump, which is always the wrong heat pump. I will use this one. It doesn't really matter actually for this purpose, but I want to have some storage tanks, a hot tank and a cold tank, and I want to have a borehole loop. And here, as you probably know, most of you, these elements have very simple parameters here on the standard level. And then you can go, as many of you have already, go to the advanced level, and the system is built for you. And the purpose of this, of course, is to simplify testing of a lot of different system combinations without having to manually connect all this by hand. If I had connected this by hand, it would have taken me, the better part of a day, I think, to figure all these control circuits and models out and connect them in a meaningful way. So it's a very good and quick way of checking that some combination of units will do some good for you. But since the real, if you would build a real such plant, you would spend a lot of time thinking about the controls and the sizing of these components. And here we want to do all this automatically. In the ESPO system, we've taken quite a lot of not shortcuts, I wouldn't say, but we're doing this in very unconventional ways. You will not see these type of connections in a real HVAC system. And so we're using these tanks here that are, we call them ideal tanks, that you can buy such tanks, but they're not very common on the market, especially not for small systems. And then we connect all of these loops more or less independently to the tanks. and these loops are also sort of self-controlled. They know by themselves by just looking at some measurements what they should be doing in order to be able to create reasonable control systems without having to build a global control system that knows what's going on in every unit, which you would have in a typical real plant. So this means that the ESPO plant is kind of quirky. You know, it's good because you can build many different types of systems very quickly, but it also uses some very unconventional ways of doing this. And it's a little hard actually to sort of incrementally build on the ESPO plant, because then you have to understand a lot of these quirky things. And so it's usually better actually to, if you have you know, a specific plant to build, to throw away the ESPO plant and start from scratch. And Jürgen will show you such an example in a moment. I will show you here a little bit what we have made in order to simplify this process of building plants at the advanced level by hand. So one of the things, or there's a lot of small things that riddle this process, and we've tried to address most of them, as I said. So one of the typical problems that you might have is that people forget to have an expansion vessel in a circuit. So here, that's also a new thing in ICE5. You can add expansion vessels to individual components very quickly, and you see that also on the symbol that it has an expansion vessel. Let's say I take away that expansion vessel, and then I do this check circuit operation. Then there will be an algorithm that finds that, okay, this particular circuit doesn't have an expansion vessel, and you can then put it back or add it if you've forgotten it. So there's several such checking algorithms. If I, for example, change the fluid of one of the components to something else, this will also be picked up by this checking algorithm. So it reports that you have a different fluid in one of these components. We can change it back. There's other rules that are set up also to avoid mistakenly, for example, connecting two given flows in series in a long circuit and so on. So there's several such rules that we have implemented that should help the modeling process in general. There's also a new palette of components. We're experimenting here with a new palette design, which is only available for the plant now. Where you can expand different sections of the palette. And we've also gone through the actual models quite a lot and supplied them with, for example, so all of the models on the palette have forms now, and it's many of them also have database support, so you can actually, instead of trying to figure out what the parameters are for many of these components, you can pick one up in the database, and all of these parameters will be furnished for you. So those are things that we think will help quite a lot. Also, you will find that the sort of quirky special ESPO components that enable this way of getting these circuits to operate independently and so on. For example, this pump and some other models are not in the palette. So that's sort of a recommendation that you shouldn't be using these components for your own modeling, basically. We call them ESPO special components. We've also begun, but not finished yet, in the beta release, a tagging system, so you will be able to sort of read some tags. They will be characterized by tags, so you can see which components you might want to use depending on what their tags are. There are some fundamental, we've gone through all of the models, but there's some fundamentally new models also. I specifically want to point out two very interesting new pipe models that Mika will show some interesting examples of for districts. So it's a plug flow bidirectional pipe flow model, and a finite difference, also bidirectional not plug flow, but finite difference model for modeling actually more realistic pipe networks inside and outside of the building. This is a really interesting model. So this is what we call a brine node. this is something that allows you to connect any number of bidirectional or unidirectional flows to such a node, and it's a very quick way of creating also very complex networks, and Jürgen will show you more examples around this. And I think I will leave it at that. We're a few minutes late still, but I think we can wrap it up in time. So Jürgen, perhaps you can take it all from here.
Yes, thanks. Yes, plant modeling. It's not that difficult as you can imagine. We usually recommend that you start a plant modeling from a template or something where you have cleaned it up a bit. You can create a template to start with just from an empty ESPO plant and build plant model and take all these other stuff away. It could be a good starting point. As I do this a lot, we have other templates that we have created. So I have something here. That's a good starting point for me. Template that is pre-prepared that I use. To build a plant, it's usually good to have a picture in the background of the plant, so a drawing. So this is the best way of doing it. So you insert new graphics and you select picture. And you select a picture of the plant that you want to model, like this. So this is a very good starting point of plant modeling. And then it's just to populate the plant with the components in the picture. But it's very important that you just do small parts at a time. So for example, if you start with this domestic hot water production, we have to have something that gives heat from the district heating, and then it's very good to use this simple boiler with one circuit like that. Then you need a pump, of course, to give some pressure, and I don't really know, but this doesn't have an expansion vessel, so I have to introduce an expansion vessel like that, and a valve that gives the mass flow like this. Let's see, this PMT control is the most common valve, so just connect these together like that, and then heat exchanger. So now it's actually the system that we are modeling like that. So actually this is the valve that should be here. So and then you just connect it together and then to the system, of course. So I made this other part just to make it sure that the system works, that I run. So like that. And as I said, it's very important to test small parts and always try to simulate. I'm lucky that it runs, of course, like this. And then you continue to build. But as you see, it's a lot of components. So a good way of doing this is actually to have pre-prepared subsystems. So you should perhaps make wall there. So I have a prepared district heating system that contains all the components that I discussed. So I just have to add the valve on the district heating. Then it's much cleaner. That's quite important. You shouldn't have more components than necessary visible in the plant like that. So, and here you also can see something that is usually quite common in my model, in my picture, is an energy meters. They are everywhere. So energy meters is also something that is good to have. So I have it here, energy meter. So just drag it as a subcomponent, submacro. That is just an energy meter, flow meter, some PMT maxes, and an output file. It's a good thing to have output files in all these submacros. If you forget to add them here, so in this view, so you always know what temperatures or flows or heat fluxes you have in the system. That's really important. So just make small systems. So if I turn this off, then you continue to make it bigger, the system, all the time. I still use this district heating to further expand the system. Now this district heating is instead of the heat pump chiller that I will add later on. So small steps. I will say this all the time. So now I have further developed it. And here is also temperature sensors. They are also everywhere. So I have the temperature sensor here and a log file for the temperature. So that's always good to have. So as you can see, you gradually build the system all the time, add one heat exchanger at a time, and then test it. Now I will show you some interesting that Per talked to you about. That is new, that couldn't be made before in IDA. So here you have possibility to add tanks in series that have different flow has flow in two directions. So if the red circuit here, the supply from the heat pump, if the flow is larger than the extraction flow in this pump, the flow will flow through the tanks in this direction. And the opposite, if the heat pump is off, no flow in this circuit, the heat can be taken from the tanks in this direction with a backwards flow. So it's really useful. And that's due to the new brine node and the tank with bidirectional flow. And if you look below here, I have also a few connections in loops. I have one separate loop for the heat pump, one for the borehole, as you can see, one for the middle circuit, and one for the cooling. So it's a lot of circuits. In earlier versions, this would have been quite difficult to model, actually. But due to the new brine node, it's very efficient to model it like this. You just add a brine node in each connection point, and then insert the pump with a valve that I have here, always a pump with a valve. So then you have separate circuits that will work independently. And something you can also see here is that I don't use the other heat expansion vessel. This is more neat. If you want it to look exactly as the drawing, you can add a tank with a built-in expansion vessel and connect it to a brine node. This will also act in the same way as using the ordinary expansion vessel. Building the piping system is just actually a small part of the problem. The larger part is usually to make it work. So then you have to have some controls. And I've usually put the controls in a separate macro. That's what we think you should do. So, and a good way is to have the control description here. I actually use this annotation and put it here in the schematics view as control description. And here on the right side of it, I have the control logic in sub macros. So this is how the outdoor air temperature, this is set point dependent on the outdoor air temperature as a curve. So I make a lot of these sub components or sub macros with some short, small control parts. So divide it in small parts as much as you can. And then, of course, it's important that you tell everybody that looks at this what you are controlling. So this actually controls VO1, SV1. That is a valve that you find here. This is the valve here, I think. That is controlled. No, this is H4 that controls that one. So yeah. So here you can see actually what module that controls what in the model. And also here's the ground source heat exchanger. Now this is one way of doing it. You have to, if you use it a lot, I recommend that you make a module of it, a subsystem. And then it's just to make the simulation, and you get the result, of course, how the heat pump works. Here you can see it's only used during the winter. It can also be used as a chiller, actually, but you have a lot of free cooling, so it's just used in short times. So if you look at the ground, for example, you can see the temperatures. When the temperature from the ground is hotter than to the ground, it's used for heating, to extract heat from the ground. And here during the summer, you have it in the opposite, so you have a lot of free cooling. To build a plant like this, if you're a bit experienced, will take a day or two. So it's not that much work, actually. And you will absolutely need it to assess the control system to see how it works together with the building and system. And
so,
yeah,
Jürgen, sorry, we are not doing too well in terms of time here.
I know that, so it's
so in order to give some time left for Mika, we have to,
yes,
to
I understand.
wrap it up.
So I'll give it to Mika here from here.
Thanks a lot, Jürgen.
So it's Mika here, and right now you can see my screen, right? Okay,
yes,
great.
Yeah, absolutely.
So we will start with some district stuff. As already Per mentioned, that we have worked with district models, and EQUA Finland has worked with in the smart autonomy project with not large scale district, but this kind of small scale district systems. And highlight of that, as already Per mentioned, that we have this finite difference model, have a bidirectional flows. That's one of the key components to be able to make this modeling for the looped and nested networks. And as already Per mentioned about the scaling, it's scale very well with the hundreds or even thousands of customers in the loop. And here we can present the two different approach. That ones that we have all the consumers network and the plants are modeled in the same model, or the other opportunities using co-simulation, that we will have a number of IDA instances and they are discussing between each other during the simulations. So this will open the demand side management and renewable energy modeling with the control strategies. And if you have big network, you can always replace the building model with some pre-calculated time series, load profiles, or measured ones. And these prototypes that I'm showing are based on Peter Knuckles' PhD thesis work and his implementation. These are prototypes. So in the single IDA instances, we made first with the data extraction from OpenStreetMap, and then it will recognize the buildings and the streets there, and we transferred that to the GGIS environment. And then in this case, in the first case, we automatically generated the pipe network, as you can see in the picture in the graph. And then we can work with the peak heat demand and simulation factors. We can optimize the hydraulic network. And if the heating demands are not known, you can quickly calculate that using AHUs. And in this Peter's implementation, there's this kind of automatic generated building model, just a few key numbers, parameters of the building, and then will be generated. And here you can see that it's in the one in either instances and in 3D with graphics, you can see that all the buildings. And here is the actual visualization. Let's see how it works with the team. So you can see that it's the beginning of the year, the 1st of January. You can see that how it's actually working between these buildings. And that green spot there is the actual plant model here. So all things this happens in the single LiDAR. And now I switch back to actual IDA here. So there's a little bit delay in the screen. Okay, now you can see the same thing in actual IDA. The previous visualization was in the PowerPoint. So here we can see the buildings, and this is campus area. Actually, this is the building that I have studied and worked in my university time. And here we can see the buildings. They are treated as a consumer with the time series, and there is a heat exchanger on the right-hand side. It's the actual building, and on the left-hand side there's a network. So these are pre-calculated or some other sources. We have got the information from other sources to actually show the buildings. And then in here we have a plant model or the heating production. And this is air to water heat pump. And then it's connected, the liquid side is connected to big tank. And actually with this tank, we ended up in this project to 15% energy cost savings once we are charging that tank in the early morning hours when the electricity price was the lowest one. So we will end it up on an annual basis, 50% savings in heating electricity with that heat pump. And this is a co-simulation system. So one of these buildings, this is a new construction. Instead of having time series there, we have introduced these import and export components, which actually defines them.
Mika, could you turn off your video? I think we're having some bandwidth problems here.
Okay, I will do that. Okay. Great. And then to open the other instances is that I will go here on the file menu and start an additional one, other one, and then I will open the actual building here like this. And then we have a building, our normal IDA building here, ICE building, but the plant, we have the same import and export as we have in the network side. And this plant is...
There's some problem with the screen, Mika. We're still seeing the network part of the system here.
Okay. In my...
There we go. Now we can see the...
Now we can. Okay. Sorry about that delay. Then this is detailed plant model, and this is designed or actually developed in the Smart Autonomy project, because the whole idea is that district is a low temperature level network, and the domestic hot water is produced in each building. And start the code simulation here is that I will start the simulation here and the other one, and then it's running simultaneously. Okay, that's the co-simulation approach, and due to time, I don't start it. So one new thing that you can find in ICE 5 is a building load estimator. Once you are making such a plant modeling as Jörgen showed, there's might be the situation that the building itself, building model itself, it's not yet done, and you have to start with the building plant simulation already. And it's crucial and very important to get the loads, building loads correctly. So now you can find from the new menu, you can find under the ESPO, sorry, this is the ICE 4.8. Let's jump to the ICE 5. So in here, the new documentation, you can find ESPO wizard, and under that the building estimator, and it's look like this. So that's a single window sheet front-end approach to make the whole building. In the building type, you can describe the internal gains, ventilation, amount, fan schedules, and also domestic hot water. And with just a few key numbers, you can describe the whole building, and then you will get the loads right for plant modeling with a couple of steps. And mostly, in most cases, the buildings are not these kind of shoe boxes. So here you can find some practical hints that how you adjust your facade area correct to model the different building with the different shapes. And here you can go on with give a more input data, and then it will transfer that one to actual ESPO model. And here you have to remove the ideal heaters and coolers and add at least the simple fan coils there, and then you can go on again to the next level to either ice, and then you have the full building there, and then you can start working with the plant modeling. Okay, then there was a couple of new features that we want to point it out at this time. And one of them is that arbitrary shapes of the window and floor heating and the wall parts. So now you can go in the, for example, on the wall, I miss it, and start editing the window shape, for example. Once you have selected it with the right button of the mouse, you can find the edit, and we can make, for example, this kind of window here. And this same functionality, it's available under floor heating and wall pieces like that. Now you can see it. It's after the delay that there's this kind of thing. And then in ICE 4.8, once you create the advanced level system, it was always the custom simulation. But now in ICE 5, you can build the model, the advanced level system for the special simulation types as well: heating, cooling, load, energy, and overheating. Right. And then if we have an plant, it's very handy to see what is actually happening here. So these line connections, these pipes, they are shown differently if there is a mass flow and if there are not. And also once you open the outline view and have variables here, and then I start a simulation here, we can see that these numbers are varying during the simulation, and also colors are changing while it's running like that. And then we can stop and evaluate the actual status of the plant, that how it's behaving. Okay, and then I will jump back to 4.8 and show the last feature that was in our list is the quantity takeoff. So I have already made a case here, which is an office building from our standard IFC model, like that. And then I have made already the energy simulation, and this is an example that now will be available in ICE5 as well. It's a quantity takeoff, and this is example to one-click LCA. And there's just selection that if you want to have include an export, include energy report or not, and this will open, generate the Excel sheet that's clickable, ready to make direct transfer to one-click LCA, for example, but it will be available to other softwares as well. Okay, that was my part. So let's switch back to Per then. Thank you very much.
All right, thank you very much, Mika. So this brings us to the Q&A session, and so let's open the floor for some questions. I don't think we have so many questions. We have only, so I can see it, one now. So it's a good thing we ran over, perhaps. Anybody that wants to ask something can. This is just Eric saying, could you make these webinars longer? Yes, we could, of course, but I guess it's also a matter of thinking about how much time of your time we could occupy with these webinars. But it's good that you want them longer. Yeah. And anybody else? Do we have any raised hands? Or?
We have a raised hand from Erik Johansson, so I'm gonna go ahead and unmute you.
Okay, thanks. Hello. I think we're not hearing Erik. Perhaps he will get his mic in order, and then we can return, or you could type your question. Is there anybody else that wants to go in between?
Okay, we have a question from Wolfgang Snell, so I'm gonna go ahead and unmute him.
Okay, thanks.
Can you hear me?
Yes, we can. Thank you.
Perfect. I typed the question already in the question section in the chat.
Right.
But
maybe I'm having some problems looking at them.
Read this. So I can tell you also. Is there a possibility to make a pipe model, not for the hydraulics, but for the heat loss inside a building? I mean, for example, when you have a circulation pump for domestic heat or domestic hot water, you get quite a lot of heat loss into the rooms. Sometimes you want this, or you can use this heat loss during winter time, but you cannot use this heat loss during summertime. This would be quite interesting to model, for example, when you have a circulation pump that's on and off during specific times a day or something like this, and then you get the dynamic heat loss of the system.
Absolutely, this is a good point, and it's on the agenda of things. It's not in ICE5 yet, and it's a little bit doubtful that we will be able to do it in ICE5. We will try, but it's certainly in the plans to be able to. Right now, as you know, the losses that are you describe in IDAR are based on this previous European standard, where it's just losses and irrespective of temperatures. And in the new edition of the standard, the temperatures of the various rooms should be part of the losses, and that would I think, fulfill what you need. And this is something that we're looking into doing for sure. It's not there yet.
Thank you.
Right. I actually found the questions now. I had some problem with finding them. Yes. So let's see. While we're waiting for Erik to get his mic in order, perhaps we can. And there was a question about shading. Is there a way to make sloped shadings? Actually, you can do that in several ways. I'm not 100% sure that you can edit them in IDA yet, but you can certainly import them if you have made them in other programs. Maybe somebody else can answer this question. I'm actually not 100% sure.
Yes, Mika here. Yes, it's doable, but I won't show it here. Mika, please take contact to me. I will show it later today. Yeah, it's doable. Yes.
Right, and then there was a question about new things around solar energy and having several plants. It's not a standard feature in IDA at this, also in IS5, to have multiple plants. There's still only one plant, but with multiple temperatures, as you saw. In the new district application that we are working on, you will be able to have any number of plants. And then we have done some new stuff on the solar energy. One thing is that we have upgraded the model a little bit to be able to handle these these vacuum tube solar heat exchangers. We've also tuned the parameters a bit to fit with a large database that is out there for solar thermal systems. Could you please show how to combine the housing and the district again? Sorry, we don't have time for that now because we only have 2 more minutes, but it's good that you're interested. We will put this in a movie, you can look carefully, and then of course we will return to these things in our courses and so on. When will IDA be available? IDA 5, the beta is available already, and it's been sent out to all maintenance customers are able to use it now. Test it. We have just recently released a new beta version, and the plan is to release it formally in the fall sometime. We haven't set a specific date for this. We actually don't set dates for our releases. So that was 3 questions.
We have another raised hand from Gustav Turesson, so I'm going to unmute him.
Thank you. Hello, Gustav.
Can you hear me now?
Yes, you can.
Oh, good. Thank you. I was wondering, have you tested the borehole model and the solar thermal against other programs to see if they calculate and get the same numbers?
Well, absolutely, yes. Both of them have been tested with various validation test cases, sure. Many times, yeah. When it comes to the borehole, it's actually most of this is a very long story actually, but the borehole model is the most commonly used borehole model is using these G functions that we are not using. And G functions is actually a severe simplification in many ways, and that the IDA model does not suffer from. So we're not trying to mimic results that come from programs that use G function approaches, basically, but more measurements and more detailed physical models. I think actually we have we have a list of questions here that we haven't been able to do here live, and I think, but I've just browsed through them, and I don't think that there's so many questions that are of general interest other than the release date. And so what we will do is that we will wrap it up here, and we will send out written answers to most of the questions to you guys. And we will just thank you for your time for the moment, and I will just remind you that there are so in this series of IDA's webinars, After we've had 5, or we will have 5 follow-up webinars from the highlights, from the ICE 5 highlights, and the 5th and last one is going to be delivered on May 4th. So you might occupy that slot in your calendar already if you're interested in this. And so I guess with that, I will thank you for your time and close this session. Thank you.